The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Let's get started. We have a lot more chemistry to learn today. And as you're probably becoming aware, the octahedron plays a very important role in the coordination chemistry of the D block elements. So we're going to begin today also with the octahedron. And I just want to remind you of the approach that we were taking on Monday to understand how d orbitals split under the influence of the presence of a set of ligands. And this splitting I'm referring to is an energy splitting. So we're talking once again about how we can use energy level diagrams to understand and interpret the properties of molecules. And today in particular, we're going to be thinking about how we can go from the angular properties of the d orbitals all the way to some of the magnetic and spectroscopic or color properties of ions that contain these D block transition elements. And so you'll remember last time on Monday, we looked at placing ligands at positions 1 through 6 on the octahedron in reference to our coordinates system that we had chosen x, y, and z here as specified. And what we were doing was at each of these positions that corresponds to a ligand atom, what we were doing is evaluating each of the d orbitals for the value of theta and phi that's found at that ligand position. And so I'm going to put up part of the table that we generated last time, and that part will correspond to ligand position, where we have ligands 1, 2, 3, 4, 5, and 6, those 6 ligand positions. And 2 of the d orbitals here, dz squared and dx squared minus y squared, were found to give non-zero values at these 6 ligand positions that correspond to an octahedral complex. The other 3 d orbitals gave 0 at those positions because all 6 of these ligands lie on nodal planes of xz, yz, and xy. And what we're doing is we're just writing down in tabular form the relative magnitude of what you get if you evaluate the orbital at those ligand positions. So we had 1 in positions 1 and 6, which are on the big lobes of dz squared along the z-axis. And we set that to 1 because that's the largest value that we get when we evaluate any of the orbitals. And then relative to that, these ligands 2 through 5 that are in the xy plane and which interact with the torus of the dz squared orbital in the xy plane have a value of 1/4 of what it is along the z-axis. Okay? And then dx squared minus y squared evaluated at positions 1 and 6 gave us a 0, and that's because positions 1 and 6 fall on the z-axis, which is a nodal, it's actually an intersection of 2 nodal planes for the dx squared minus y squared orbital. And then here we have at positions 2 through 5, 3/4. And if you're having trouble understanding what these numbers mean, remember that we started out with a sphere. So we're interested in seeing essentially what's the probability of finding that electron in that particular d orbital at that point on the surface of the sphere. And so what this is saying is that, if you will, the radial probability of finding an electron in dz squared along the torus at some distance from the center is 1/4 of what it is along the z-axis at the same distance from the center. And then in the case of at that same distance, if we are in the xy plane along x or along y, because that's where the lobes of dx squared minus y squared extend, that probability drops to 3/4 relative to the two big lobes of dz squared along z. So you can think of it as telling you about the size of the lobes. And accordingly, the way that these lobes of the d orbitals can interact with the ligands at these positions on the surface of the sphere, coming right out of evaluating the angular parts of the wave function. And then there are other important coordination geometries that we have to consider, because coordination number 6, which corresponds to the octahedron, is relatively common, but coordination number 4 is also quite common. And one of the important coordination geometries for coordination number 4 is a tetrahedral coordination geometry. So the tetrahedron is not limited to being important in organic chemistry. It's also important for coordination chemistry. And you'll recall that when we look at a tetrahedron, we talk about ligands at alternating corners of a cube, and I'll call these ligand positions 7, 8, 9, and 10. And if we have a tetrahedral metal complex with 4 ligands, be they water ligands or chloride ligands, and be the central metal ion something like cobalt-2 or nickel-2, then a tetrahedral array like this is produced. And we can go ahead and evaluate the d orbital wave functions at theta and phi values that correspond to these positions 7, 8, 9, and 10, all at the same distance from the center. And then we can generate a similar table where we have our ligand position and our set of d orbitals. And I'll start here with dxz, dyz, and dxy, and over here dz squared and dx squared minus y squared. And we need our ligands positioned at 7, 8, 9, and 10, which are these alternating corners of the cube, which is the tetrahedral geometry. And what we find when we go through and evaluate for those theta and phi values that correspond to these ligand positions using our polar coordinate system, and then scaling it the same way that we do over here for the octahedron, we'll find that all of these values come out to be 1/3. Notice that in the case of the octahedron, we're interacting with some of the lobes, like the lobes of dz squared, the large ones, directly along the axis that makes it a pure sigma interaction, a cylindrically symmetric interaction. Big lobe of dz squared and a ligand coming in along the z-axis. But if you think of the positions of the lobes of the xz, yz, and xy orbitals relative to these ligand positions 7, 8, 9, and 10, the interaction is kind of oblique. Okay, it's not 0, we're not on a node, but it's pretty small. The overlap isn't going to be as good. And it evaluates to a 1/3 for all of those positions. So what we find is that while xz, yz, and xy were all 0 over here for the octahedral case, over here for the tetrahedral case, they're all the same again, but they're not at 0, they're at 1/3. And then for x squared minus y squared, remember x squared minus y squared has its lobes along x and y. And what that means is that ligands 7, 8, 9, and 10 actually lie on a nodal surface of the dx squared minus y squared orbital. And that means that this is 0, this is 0, this is 0, and this is 0. And the amazing thing about the math of the tetrahedral geometry is that these ligands 7, 8, 9, and 10 also lie on the nodal surface of dz squared. Remember that dz squared looks like this and we have our opposite phase torus in the middle, and then we have a conical nodal surface. And we actually went ahead and if you set dz squared, the equation for dz squared equal to 0 and solve for it, we found this angle here. We found that angle. And you'll remember that that was the arc cosine of root 3 over 3. Okay? Turns out that value is exactly half of the tetrahedral angle, which is the angle between 7, the center, and 8. And because of this, all ligands 7, 8, 9, and 10 lie on the conical nodal surface of dz squared such that we get zeros here too. So one thing that relates very nicely the orbital picture for the tetrahedral case to that for the octahedral case is that z squared has the same energy as x squared minus y squared when you sum over all the ligand positions. We're going to get 3 here, and we're going to get 3 here. And xz, yz, and xy all have 0. And over here, xz, yz, and xy all have 4/3. And z squared and x squared minus y squared both have 0. And so I'll redraw that over here. So what we're doing is we're drawing up d orbital splitting diagrams for 2 different possible coordination geometries for a coordination complex. Let me just make that very clear. And I have my energy units here, 0, 1, 2, 3. And this energy level diagram looks like this for the octahedral. And we symbolize the octahedral geometry with this OH for octahedral. And we have here an energy splitting. We have a triply degenerate set of orbitals, which we recognize as xz, yz, and xy. And the name that we give to that triply degenerate set is T2G. Okay? This T2G triply degenerate set, so this whole set is the T2G set. If I use that word, that label, T2G, you should remember the specific d orbitals that contribute to the T2G set and make up the T2G set. Up here, we have the dz squared and the dx squared minus y squared at the same energy, which is 3 relative energy units here. And those two together constitute the EG set. And I'll often write that with a star because we're going to find out later when we do the molecular orbital theory of coordination complexes that these are antibonding. And the reason they're antibonding is because if you go over here and look at it, if you have a ligand that wants to act as a Lewis base with respect to dz squared, then putting an electron in dz squared leads to repulsion of that ligand, generating antibonding character. So you want your Lewis acid to have empty orbitals to receive lone pairs of electrons. And if instead they're populated, that corresponds to antibonding character, much like we've talked about for other types of molecular orbital diagrams. This d orbital splitting diagram for OH is really a simplified molecular orbital diagram for the molecule in which we just look at those orbitals that derive from the set of 5 d orbitals on that metal ion, because these are the orbitals and together with the electrons that occupy them that control the properties of color and magnetism that we'll be talking about for the rest of today. And let me remind you here that we have a name for the magnitude of this splitting, which is called delta O for octahedral. And then we also have the tetrahedral case. And How do we get the diagram from this? We just sum over the contributions from each of the ligand positions. In tetrahedral, there are only 4 ligands. So we have, for XZ, YZ, and XY, we have to sum up 4 times 1/3. And that gives us, for that set of 3 orbitals, using the same energy scale as over there, 3 orbitals at a value of 4/3, and 2 orbitals down here at our 0 of energy. And these will be dz squared located on that node, and x squared minus y squared. Whereas up here we have xz, yz, and xy. And these get the names E and T2 in the tetrahedral geometry. And the splitting between the levels, the doubly degenerate and the triply degenerate pair of energy levels, is here referred to as delta T. And from the math of these 2 tables, and the magnitude of this splitting being 3 relative to this one being 4/3, you can easily derive the relation that delta T is equal to 4/9 of delta O. Okay, so one of the neat things about this result qualitatively is that if you have more ligands, 6 versus 4, you have a larger splitting of the energy levels. And that corresponds to putting more Lewis bases, more negative charges around that sphere that we talked about in the coordination sphere. And also, if you have interactions between ligands and metal d orbitals that are, end-on sigma symmetry directed at each other, you get bigger splitting, because that leads to better overlap than the type of oblique overlap that you get if you have a ligand at a position such as 7 relative to an orbital like dxz. Okay? So you can now see that to fully appreciate this, you really have to have a very good grasp of the nodal properties of the d orbitals. And this is why I'm going to re-emphasize that you should spend some time on the computer visualizing these things and rotating them around and seeing where these ligand positions for these different coordination geometries are with respect to each of the 5 d orbitals. Okay? That's quite important. Also, you're going to see that you could consider other possible coordination geometries that involve ligands at these positions or at other positions. For coordination number 5, you could have a trigonal bipyramid coordination geometry. And you could go ahead and evaluate the d orbitals at the relevant positions. You would already have 3 of them here, because in a trigonal bipyramid, you would have ligands at positions 1 and 6 and 2, and then 2 more back here at 120 degrees to 2, but in the xy plane. All right, so you can do a trigonal bipyramid the same way and generate the d orbital splitting diagram for it. You can also go ahead and do a d orbital splitting diagram for a different geometry corresponding to coordination number 4, which would be the square planar coordination geometry. If you just took ligand positions 2, 3, 4, and 5, you could generate a diagram. And that diagram would be relevant for systems that do have square planar coordination around a metal center. And these are actually fairly common. So those are all, those are 4 coordination geometries: octahedral, tetrahedral, trigonal bipyramid, and square planar, that are all pretty commonly encountered and that you can actually interpret pretty nicely using the d orbital splitting diagrams. Now, one of the properties that we're going to want to interpret will be the magnetism. Okay, and in talking about the magnetism of coordination complexes, we're going to start by mentioning two terms that you've probably heard, but I'd like to define them explicitly today. One is paramagnetic. That term is given to substances that are attracted into a magnetic field. So it's somehow a bulk phenomenon that we're going to relate to properties of d orbital splitting diagrams. And systems can also be described as diamagnetic. And there are many other types of magnetic behavior that we won't be discussing. Okay. I'm a little too close to the board here. Diamagnetic. And that means that the substance is repelled out of or away from a magnetic field. Okay, and one thing that you should keep in mind is that the magnitude of paramagnetism is usually orders of magnitude greater than the magnitude of diamagnetism. This is much larger. And what this means is that if a substance behaves as a paramagnet, you can often neglect its diamagnetism that also may be present, also must be present. So substances that are paramagnetic are also diamagnetic, but the paramagnetism is much larger in terms of its order of magnitude and wins out. Okay, so if you want to measure one of these quantities for a system, that which is far more difficult to measure is the diamagnetism because it's a much smaller number. And then I want to bring up this quantity S. This is the spin quantum number. And you can readily calculate S from looking at a populated d orbital splitting diagram, because it will be the total number of electrons multiplied by 1/2, which is the spin per electron. Okay, so if you're confronted with a particular coordination complex, the kind of thought process you'll need to go through is, okay, what's the coordination number? What's the coordination geometry? What does the d orbital splitting diagram look like? How many electrons do I have with which to populate the d orbital splitting diagram? After I've figured out how to populate the d orbital splitting diagram, how many of those electrons are unpaired? That gives me this. I can then calculate S. And if I have S, I can make a prediction about the value of something called the spin-only magnetic moment. Let me mention one more thing back here, and that would be the units. When we talk about magnetism, we're going to be using units of this will be the Bohr magneton. It's sometimes written as mu sub b. It's also sometimes written as capital B, capital M. Okay, that's the Bohr magneton. And it is equal to 9.2741 times 10 to the minus 24th joules per Tesla. Okay, so this is the value of the Bohr magneton, And the Bohr magneton is the unit also of our magnetic moment. And in particular today, I'm going to be talking about the spin-only value of the magnetic moment. So we're going to be making predictions using spin-only considerations. And for those considerations, we need to be able to calculate S. And we can do that pretty quickly after we've got a correctly populated, correctly chosen d orbital splitting diagram for the system. And so the spin-only value for the magnetic moment is given by this formula, which is mu is equal to 2.00 times the square root of S times S plus 1. Okay? And in this formula, this part, this square root of S times S plus 1 from the quantum mechanics is the value of the angular momentum. The electron spin, angular momentum. And this value, 2.00, I'm calling it 2.00. It's actually a number that differs only very slightly from 2. So we can, for most purposes, use 2.00. This is called the gyromagnetic ratio of the electron. And as its name implies, it's the ratio of the angular momentum to the magnetic moment for the electron. So this is our conversion factor to go back and forth between angular momentum and magnetic moment. And that factor is the gyromagnetic ratio for the electron. Okay, you'll see this as gamma sometimes. And for the free electron value, it is a number very close to 2. And so if you think about different ions that could be at the center of a coordination complex, you wonder, well, what are my possible values for the spin-only magnetic moment as given by this formula? Well, if we can make a table for that. We have the number of electrons that are unpaired, remember? And then we'll be able to calculate S, and then we'll want to get mu, which is this spin-only value calculated according to that formula. And ions from the part of the periodic table that we may consider working with can have 1, 2, 3, 4, 5, 6, up to 7 unpaired electrons. Okay? These numbers like 6 and 7 are more important for the lanthanide ions in systems with F electrons than for systems with D electrons. But nonetheless, we can easily make these predictions the same way. And so S would be 1/2 for 1 electron, 1, then 3/2, then 2 for 4 unpaired electrons, then 5/2 for 5 unpaired electrons, then 3, and then 7/2 finally for 7 unpaired electrons. And if you put this into this formula, you would see that for 1 unpaired electron, it would be 1/2 times 1/2 plus 1, square root, times 2. That would be square root of 3. So this would be a spin-only magnetic moment of 1.73. Okay? And then for S equals 1, we actually have a value of about 2.83. And then for 3 unpaired electrons, we have a value of 3.8, let's say approximately 3.87. And then for S equals 2 or 4 unpaired electrons. We have a value of 4.90. For the spin-only magnetic moment, if you go through with these values of S, these numbers of unpaired electrons, let's just make sure we're very clear on that. And then 5.92, 6.93, 7.94 approximately. You can check those numbers, but they're approximately right. And in each case, what you're seeing is the spin-only prediction for the magnetic moment is always, in units of Bohr magnetons, a little less than 1 plus the number of unpaired electrons. Okay? So it's not like you have 4 unpaired electrons, so your spin-only magnetic moment is around 4. It's actually a little less than 5. Okay? And that's because of the quantum mechanics of the electron spin angular momentum. And this kind of consideration here leads you into thinking about what happens with different dn counts for a particular type of metal complex. So this means that we're going to attack and address the high spin, low spin problem. These systems are not so terribly difficult, but let's face it, once you have been presented with a particular coordination complex and you think you know the geometry, and you think you know the d orbital splitting diagram that corresponds to that geometry, and you think you know how many d electrons go into that diagram, there's one more thing, and that is that sometimes you have to figure out if it's high spin or if it's low spin. Okay? And what that means is, for a particular dn count, there might be 2 possible choices over here, depending on how the electrons occupy the orbitals. And so let's look at an example of this. Here's energy. This is again, we're really focusing a lot on energy level diagrams. Sometimes we focus on molecular orbital diagrams. Right now, we're using these d orbital splitting diagrams. And I'll give you an example that is octahedral. And this is a species that we looked at in a recent demonstration in class, which is hexa-aquo, meaning 6 waters around an iron 2+ in an octahedral array. Okay? This will be our metal complex, for which we will draw the d orbital splitting diagram. It's an octahedral complex, so we draw our diagram like this. Okay, and of course we have T2G and EG star levels that we can populate with our d electrons, and we're going to need to figure out how many d electrons we have to put into this diagram for the octahedral system. Okay, the oxidation state of the iron here is +2. Okay, and you can tell that because the way you tell oxidation state is to take into account both the charge on the ligands. Chlorides, for example, are -1. Waters, because water is a neutral molecule, is simply neutral. And then you have to also take into account the charge on the whole ion. So this is iron 2+, the iron in the +2 oxidation state with 6 neutral ligands. If I had 6 NH3 ligands and the same charge on the ion, then it would still be iron +2. Okay? And you're going to get some practice figuring out oxidation state, because if you can't do that correctly, you can't identify the number of d electrons to put into the diagram correctly. And this is iron plus 2. You need to know that iron is in group 8 of the periodic table. So the equation for number of d electrons here is 8 minus 2 equals 6. Okay? It's in group 8. That means an iron atom has 8 valence electrons, the same way that carbon has 4 valence electrons or oxygen has 6 valence electrons. And in group 8 of the periodic table, we're subtracting 2 from the 8 valence electrons because there's a 2 plus charge on the system. That leaves 6 valence electrons on the iron. And that means this is what we call a D6 system. By convention, we are considering all the valence electrons that remain after the metal has been oxidized to plus 2 as d electrons, meaning they're going to go into our d orbital splitting diagram. Now, the reason we do this, in fact, is because in ions like this, the d orbitals are the orbitals on the metal, on the iron, that are the lowest in energy. There are, in the case of iron, iron has principal quantum number 3. There's also a 4s and a 4p set of orbitals available to iron, but they're much higher in energy. So we're simplifying the system and just looking at what happens with the 5d orbitals, which are the lowest valence energy orbitals available to the iron. Okay? So just like a carbon has a 2s and a set of 3 2p orbitals, an iron has a set of 5 3d orbitals, a 4s, and 3 4p orbitals. But those s and p ones are higher, so we're just focusing on our d orbitals here, using our d orbital only splitting diagrams with which to populate, with which we have 6 electrons for population of the diagram. And so what you see is immediately you'll identify with the notion that there are 2 ways to populate this diagram with 6 electrons. Because we can do this. Here we're following Hund's rule of maximum multiplicity, trying not to pair up any electrons until we run out of spots for them, and so we have to. There's one way to populate the diagram. 2 electrons in EG star, 4 electrons in T2G, one of them spin inverted relative to the other 5 because you can't put 2 electrons in the same orbital unless they have different spins. And finally, we could populate the diagram this way. Okay. The case on the left is what we call high spin. The case on the right is what we call low spin. And as you think about it, you'll realize that the high spin, low spin problem only arises for certain dn counts. It doesn't arise, for example, for d1, because we would just have put 1 electron down here in T2G, and that's not a problem. Okay? And you'll see that as you run through the D1 all the way up to the D10. So dn counts can go from D0 to D10. And that's the limit of the possibilities here. D0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here I've chosen a D6 case to illustrate the high spin versus low spin dichotomy. And you might wonder, when do you, well, okay, let me get back to that in a moment. Let me just say here that we have 4 unpaired electrons in D6 high spin. We have 1, 2, 3, 4. So that makes this an S equals 2 case. And over here we have S equals 0. And so this one on the right, this low spin case, is S equals 0. So we would say that this is not paramagnetic. It's going to be only diamagnetic. It has no unpaired electrons to give it a magnetic moment according to the spin-only formula that we looked at over here. On the other hand, over here, we have an S equals 2 state that predicts a magnetic moment of 4.90 Bohr magnetons. And experimentally, mu was found for this system to be 5.1 Bohr magnetons. So we say this one turned out to be high spin. Okay? And in a little while, we'll be talking more about what are the physical factors that determine whether a system is low spin or high spin. Remember, we have this delta O here. Okay? And there's not one value for delta O, and this is something I'm going to emphasize again in a moment. Delta O varies according to a number of factors. And these factors include the specific nature of the ligands. It includes the charge on the metal center. It includes the specific metal that you're using. Okay? And at some point, if delta O gets bigger and bigger and bigger and bigger, and exceeds what we call the pairing energy, this pairing energy is something I'll talk more about later, but it's the energy required to put two electrons in the same d orbital. So if you get to a condition where delta O is greater than this pairing energy, in other words, there's a big splitting between T2G and EG star, then the electrons will prefer to pair up down here in the T2G. Whereas if you think of it going to the limit of an infinitely small delta O, they would have S equals 2, because the gap between T2G and EG star in the limit of a vanishing delta O, for example, when ligands go to an infinite distance away from the metal center, they would then in that limit have all 5 the same energy, and so your S would naturally equal 2. Okay? So if delta O is much greater than the pairing energy, giving a large value of delta O, then that favors low spin. Okay, so factors that give rise to large values of delta O favor low spin. And I'll talk about a few more factors like that in a moment. So here's a brief introduction to the magnetic properties of coordination complexes, and I want to show that we can use the same types of diagrams to talk about the colors of transition metal complexes. So we looked at the color change in that demonstration that I showed you, and one of the really fascinating aspects of transition metal chemistry is the colors that arise because of absorption of a photon coincident with promotion of an electron from T2G to EG star. And so we'll talk briefly now about electronic / absorption spectroscopy. And the most important thing I want to impart to you here is a selection rule wherein delta S is equal to 0. Okay. This is the spin selection rule. And this means that when a photon comes in and interacts with d electrons in a system of the type we're discussing, that photon can be absorbed coincident with promotion of an electron from T2G to EG star, as long as it doesn't violate this spin selection rule. And that means that the number of unpaired electrons should be the same in the system before the photon is taken up as it is after. And so here's an example of that, a simple example. Here's an octahedral system, titanium with 6 waters and a 3+ charge. Titanium is in group 4 of the periodic table. Our water ligands are neutral. With 3+ charges to be subtracted from 4, we have a D1 system. This is one of the simplest cases for talking about electronic absorption spectroscopy, and it's the first thing that you encounter in your textbook. By the way, let me just remind you that right now you should be reading chapter 16 in your textbook that deals with coordination, chemistry, electronic structure of D-block elements, colors and magnetism, and so forth. And the ground state here is one in which T2G has a single electron in it for this D1 ion, and EG star is vacant. And if that system, in the case of titanium-3 aqua and aqueous solution, it's a pale blue color, a pretty pale blue. If a photon comes in of the appropriate energy, delta O, to promote the electron into EG star, then that transforms the system into an excited state as follows, with a configuration T2G0 and EG star 1. Okay? So these diagrams, just like the molecular orbital diagrams we developed for diatomic molecules, can be associated with configurations. And this transition can be written as T2G1 EG star 0, photon in, electron promoted into EG star, T2G 0, and EG star 1 now corresponding to the excited state. And this excited state is produced in a vibrationally excited manner, and it and the ground state interact with the environment in different ways, such that the absorption spectrum for a system of this type gives rise to not a sharp but a broad peak. And in fact, the spectrum would look something like this, going from 200 to 700 nanometers in wavelength. You would see a profile like this with one broad peak somewhere in the red, such that we leave behind the pale blue color of these solutions of aqueous titanium-3. Okay, so this would be an absorption spectrum, and this is wavelength down here. And this is the peak for what we call this DD transition from T2G to EG star. And there are a lot more subtleties on this, which is where I will begin on Monday. So have a great weekend.